where each of this corresponding file is divided into segments, and there can be different versions of the same file encoded in different rates, and based on the feedback received from the dash client. So for example, there is an MPD delivery happening from a particular file format in a particular, let's say, representation. You can easily say like resolution, for example, it's in particular resolution. And then based on this MPD delivery at the dash client, where please note this HTTP server, for example, you can imagine this running on the YouTube server, and this dash client is running, for example, in our browser or in our mobile phone, right? In the application in the mobile phone. And there are several control heuristics already available as part of this dash client, where they process the MPD parser, they send it to the media player, whichever media player we are using at the client side. And then from this MPD parser, we parse out some segments, and correspondingly, this HTTP client can send some feedback, which is like a fetch request that, I want this particular segment next from this particular MPD representation. And it's a very useful format for internet, because this kind of a fetch kind of an architecture works out really well, especially when there is some sort of dynamic nature available, or there is some non-static behavior exhibited by the network. So even in our typical network scenarios, especially for if you recall, some of you may recall, for example, for 3G networks or even for 4G networks in poor coverage, the network characteristics can change drastically. Even a small movement in the device or a small movement in the nearby environment can affect your signal quality. And then even if you're playing a HD video and everything will go on fine, all of a sudden it can happen that there is an outage and there is some sort of rebuffering happening. Now that leaves a very bad taste in terms of quality of experience for the end user, because nobody wants to see that the round whirlpool kind of thing going on in YouTube, where video is not playing. All of a sudden from HD, there is nothing playing, and you have rebuffering happening, and that really is upsetting, because at times you are watching some interesting content, and all of a sudden there is some rebuffering instance happening in the network, and it affects the quality of experience. And that is one of the motivations of this particular research, how to capture that, how to really capture this kind of rebuffering instances in our quality of experience for end user who is consuming the video. And at the same time, how can we use it to improve or enhance this quality of experience, to minimize such rebuffering instances, and what are the ways forward, right? So those are the kind of broader questions we'll try to look at as we go forward in this particular session. So given a dash kind of an architecture, which is a standard architecture already used in practice, for example, YouTube is one example which is using it. In terms of wireless video streaming, there are multiple things we need to be careful of. This is very different from your standard home network using fiber optic or even using Wi-Fi, for example, because now with the reasonably better Wi-Fi standards coming up like 802.1 AC and all, the amount of changes in the network, unless there is some core network issue or there is some backend issue in your network service provider or internet service provider, by and large, even Wi-Fi is now quite a stable network, right? And the same is not true for cellular because of varying environment and other changes. Now, in terms of typical wireless video streaming, one key aspect is time varying channel conditions. So there are three entities here. We have a transmitter, we have a receiver, and we have the channel. Typically, if you're looking at transmitter for downlink scenario where we are consuming the video on our device, the transmitter is not changing much. By and large, the base station is where it is, it doesn't move, or your Wi-Fi access point is where it is, it doesn't move, right? So transmitter is not the entity causing the changes, but the receiver can move. There is definitely mobility at the user end. So if you're using a mobile phone, or even if you're using a laptop in a home environment, you can roam around, right, with the phone or the device you're using. So there is a movement of the receiver in this case, and the moment the receiver moves, it affects the channel conditions based on path loss, based on fading, based on all the typical culprits. In the wireless scenario, the channel condition can change. So the channel is time varying. That is one reason, because of the receiver being mobile. Second thing is, even if the receiver is not moving, the surrounding can change. For example, if I am sitting in my room trying to consume this particular video content, maybe people around me are moving. That affects the signal quality to a certain extent, right? So we have time varying channel conditions which need to be captured if you want to analyze wireless video streaming. Second thing is, the resources are typically limited and they are shared. Now, but of course, a lot of you may come back to me saying, we are talking about 4G and now 5G. where are the limited resources? Resources appear to be huge amount of resources are available. But let's go back to the slide, right? Just for sake of understanding, please note, if you're looking at a UHD video, we're looking at 18 megabits per second. If I characterize a 4G downlink, a typical 4G downlink is maybe around 100 megabits per second. Right. See, with 20 megahertz spectrum, you also have to do it from 20 megahertz spectrum perspective. If you look at typical ballpark numbers, it directly translates to roughly 20 megabits per second. You can use higher order modulation schemes, but then they may not always be possible for all the users. So effectively, even if let's say we are using a very higher order modulation scheme in a 4G with 20 megahertz spectrum, we may be looking at around 5 times that, so 100 megabits per second. With 100 megabits per second kind of downlink available, we can serve maybe 5 users or 6 users with ultra HD content. But that's a really small number, because if you look at the total number of users connected to a 4G base station, the number can be something as close as 100. So with 100 users, there is significantly lower amount of resources available per user. With 100 users, right, we have hardly 1 megabits per second. So that is something we need to be careful of in terms of available resources. They are really constrained even in 4G scenario, and this is going to continue. It is not that in 5G this problem will be resolved. See, it's a question of supply and demand. We get used to the kind of network we are being served, and we correspondingly increase our demand. So if you recall, I don't know how many of you, maybe at least those of you who are faculty and all, has definitely used the 2.5G GPRS for internet connections and all. So you must be recalling those days where small video content, very low resolution, would take ages to load on a mobile phone, right? And now things have improved in terms of available network infrastructure, but correspondingly our requirement has also improved. The demand has also increased. Instead of consuming HD videos, now everybody wants to consume HD videos on mobile phone itself. So it's a cat and mouse kind of a game, where I think as we go towards 5G, we will be moving more towards 4K video. And there is also a lot of work happening in virtual reality and augmented reality and all that is going to further clutter the network. So it's not that resources will increase and demand will not. Demand typically outpaces. It's always when there is demand, sufficient demand available from business perspective, that people are ready to invest in this kind of technology. For example, for spectrum perspective, if you look at it, the 20 megahertz spectrum is few hundred, if not 1,000 crores in India. That's a huge amount of cost, huge amount of investment, right? So unless there is a huge demand available from consumer side, people will not make that kind of investment, right? So the resources are typically constraints. They are limited and they're always shared. They can be shared openly for a Wi-Fi kind of architecture without any licensing cost, or for a cellular architecture, they are in scheduled mode. Nevertheless, they are shared in some form or the other. For example, maybe in 4G, we are using OFDMA kind of sharing mechanism for resource allocation, but it's definitely there. So these are the two key constraints we have from wireless video streaming perspective. Now, from a client side, if you look at client-driven streaming based on QoS heuristics, they can be based on throughput, they can be based on buffer level, they're based on delay. So those are some of the objective metrics which have already been used traditionally for client-side driven streaming. Where a client-side, for example, a client-side dash client, it tries to use these and can, based on that, decide which segments to fetch. Right. So this kind of work has already been done in the literature. But please note, this data transfer which is happening, which is agnostic to your video transmission, can be suboptimal. Because if you are only requesting segments based on my throughput available, based on the delay available, and we are not looking at the content, we are not looking at the quality of experience the user is going through, then this is a suboptimal way of doing it. Because at the end of the day, our aim is not to maximize the throughput and minimize the delay. When somebody is watching a video, the aim is to maximize the quality of experience, enhance it to the best possible levels. And that is where this particular work fits in, where we talk about quality of experience instead of quality of service, like throughput and buffer levels and delay for resource allocation at the end. As I've already highlighted, quality of experience is not the same as quality of service. For quality of service, we can have different existing streaming strategies. In the interest of time, I'm not going through them, but you can go through some of our papers where we clearly highlight some of the state-of-the-art quality of service-based techniques. And it has also been highlighted in recent works that quality of experience is really important. That is why ITU itself has been working in that direction, in the direction of quality of experience for a while, in defining what are the key requirements. And overall, you can say it is the acceptability of an application or service. right? It's not just for video users. We can define qualitative experience for anything, any experience that a user is going through. What is its overall acceptability, right? From an application perspective or a service perspective, as perceived subjectively by the end user. Here, this perception and the subjectivity part is really important, because that is what we try to capture, and that is where machine learning comes into play. Because to capture this subjectivity, traditional models are not very straightforward, whereas from a machine learning perspective, much easier to capture it. At least that is what we will try to claim and show going forward, right? Now, this qualitative experience can be defined by various factors. For example, the actual objective video characteristics like resolution, encoded bitrate, etc. But it also is affected by cognitive factors, like what was the variability in perception, of the quality. Was there memory present in the system, right? Now, there are several existing QoE models which are also present, but they do not necessarily evaluate the perceptual QoE. And we are more interested in capturing this perceptual QoE. And we can also look at overall QoE. There are works which say, okay, if I transfer this video in this particular setup on this kind of a network in this particular resolution and encoded bitrate, you rate it at the end. Like for example, when you rate Netflix videos, at the end you give it a rating 1 to 5. That's an overall QoE, where you're essentially giving your subjective evaluation of the video. It can be a function of what was the content. It can also be a function of how it was represented, which network you are viewing on, which device you are viewing on. So there are a number of things playing their role here, and all that when we use it for an overall QoE, an MOS kind of a setup, we don't necessarily capture the streaming QoE. We are only capturing for the whole content. So please do not confuse overall QoE as the streaming QoE, right, or the continuous QoE. And in this work, we are interested in a continuous QoE, because at the end of the day, if you want to do resource allocation in a dynamic fashion, we need to know what is the current QoE experienced by this particular user, and accordingly we need to plan, right? So with that as the background in terms of how to define QoE and how to differentiate it from quality of service, let us go slightly more into details of quality of experience. So when we say perceptual quality of experience, we are typically dealing with a non-linearity. This qualitative experience for video users is typically non-linear in nature. Right? Also, it definitely has some sort of memory effect or hysteresis effect. Based on how was your experience in past certain amount of duration, it affects your current experience also. If past experience was bad for a while, even if the current 1 second video is good enough, you still have that past experience. That hysteresis is always there in a human mind, right? So the past, it's very difficult to segregate out past from the present, and that is why capturing this kind of a hysteresis effect in the QoE perceptual QoE measurement is also really important. Now it can be determined by 3 major factors. One is the source video quality. Definitely, if the source video quality is poor, the qualitative experience, perceptual qualitative experience will be poor. If source video quality is high and good, perceptual qualitative experience will be good, right? Second thing is the time varying quality, right? With respect to time, how was the quality varying? If the channel condition was varying and I was trying to adapt to the channel condition and requesting different rate encoded segments, how does that varying quality affects my perceptual QoE? That is something I should be capturing. And the third thing is the rebuffering instances, because they really are a dampener in the overall experience of things. The one thing that really kills the quality of experience is when there is no video to play, because you're essentially looking at a blank screen, and that is where we have a really bad quality of experience for any such video being played on the internet, right? So with these 3 things, now we want to capture them. And to highlight the source video quality, for example, here, as you see, there is a pristine original video, and then as we keep reducing the rate from 400 kbps or 100 kbps, there is a significant degradation in the video quality. And this can be objectively measured also, right? Because it's dependent on the rate of the video, and you can very easily see from observation also that the left bottom corner is the highest resolution. But of course, I'm not going to play here the videos. Anyway, I don't have the source videos available at this point of time. But just to highlight, I'm just projecting the image to differentiate based on different rate encoded. So for example, for 400 kbps, there is a degradation in performance, and then for 100 kbps, there is a significant degradation in performance or the quality of experience, right? So it is definitely is a function of the source video quality. Second thing is the time varying nature, right? So there are studies, some existing studies which have tried to measure this time varying nature, and they have also come up with some suitable metrics. For example, a subjective measurement of time varying quality has been referred as time varying subjective quality, TVSQ, right? But please note this TVSQ is not the same as this STSQ, where in STSQ we are capturing instantaneous video quality using some VQA metrics. So there is already a database available, live QoE database available, which was there at that point of time when we started this particular study, and we tried to capture it. And as you see here, we have an objective kind of a measurement, STREDD, and then this TVSQ is there, and then this 95% confidence interval is essentially if you conduct a study of this kind with end users and they rate the video quality. So within 95% confidence interval of this, you can see most of the time it is capturing, the TVSQ is able to capture the subjective video quality reasonably well, right? So it already existed. There was already a way to capture this time varying quality of experience. And the way it worked was you have your quality varying video. There are some STSQs prediction engines, right, which keep predicting your STSQs per second, for example. And there are models, dynamic system models, which capture this, use this STSQs, and then try to predict TVSQ. And then based on this TVSQ, we can try to decide. We can fetch, for example, the next segment based on this TVSQ. That with the current TVSQ and with predicted TVSQ, maybe this is what we should be requesting for, right? And this was a existing model at that point of time where the nonlinearity, input nonlinearity was captured in the STSQ prediction engine, and there was an IIR filter, right, which was used to predict the output, and there was an output nonlinearity in between, right, which captured the relationship between these STSQs and the TVSQ. Again, this is the work by Chen and others. Now, in terms of performance, if you look at in terms of various performance metrics like RMSE, OR, SROCC, or LCC, as you see here, there was existing works like STRED, SSIM, NIQE, and there was reasonable performance. It's not that they were not able to capture the video quality; they are able to capture the video quality, reasonably well in these works. But then one thing, so that is that was going well. But one thing that was not captured by these models is the rebuffering instances. So that is something that was not available at that point of time. And also, please note this TVSQ, which is being used. There was no existing study obviously it's around 2014, 15 time frame. So around that time period, there was no other group which was trying to capture rebuffering in quality of experience for video users. So that was one thing that we thought that maybe we should look into, and we should try to see how to do this better, right? And so for that, we looked at this work. This was a preliminary work that we had published in WCNC, where we said, fine, let's say we have a video source, we have some sort of a content delivery network, and there is a rate adaptation happening at a proxy server. And based on this, we try to do some sort of QoE based streaming, and we decide we perform resource allocation also at the eNode B using this video, which is getting a stream which is being allocated based on the quality of experience of the end users, right? And in this eTVSQ, which is kind of like an enhancement of existing TVSQ work, we essentially said, if we have data for time varying quality, plus if we have the data for rebuffering instances, can we use it to predict continuous QoE? So we are now trying to capture two type of behaviors. We are trying to capture time varying quality, and we are trying to capture the rebuffering instances. Maybe I'll take a short pause just to check if I'm audible, if everything is going fine in the connection. Can somebody give a feedback? You can type it in the chat window or unmute and share if everything is, if you am audible and if the slides are visible. Hello. Am I audible?
Yes, sir, you are audible.
Sure. Thank you. Thank you. So this kind of feedback maybe at 40, 50 seconds is also important. Thank you, Himani, also for the feedback in the chat window. Because sometimes, you keep speaking and there is a rebuffering instance happening at your end and I would
Yes, sir.
never know.
Yes.
So yes, thank
Yes,
you.
sir.
Okay, so let's continue. So now we are trying to capture the time varying quality and trying to model rebuffering into that, setup, and then compute continuous QoE. And because this was one of our preliminary works, we said, fine, typically in the network we're looking at these exponential kind of delay or exponential kind of decay models. So based on that, we came up with this model of STSQ, that to predict STSQ, if there is no rebuffering, the STSQ model remains as it is. The way we are predicting, we continue to predict it in the same fashion. However we are computing STSQ, you keep computing it as it is if there is no rebuffering. However, if there is a rebuffering happening, then essentially the quality of experience should drop, and it should drop exponentially. So that is why we added this factor of e to the power minus lambda delta TB, where this delta TB is the duration of rebuffering instance, right? And we said this rebuffering instance obviously beyond a certain point. So if there is a minor rebuffering instance, maybe the quality of experience will keep dropping. But after a point, the student simply, or the, I shouldn't be saying student, I should be saying the end user or the consumer or the viewer, they simply give up. So then beyond a certain L, it doesn't matter how much rebuffering has happened. There is a huge drop e to the power minus lambda L, which has already happened, and that is where we threshold, right? Also, after a certain point, the predicted STSQ is not a function of what was the STSQ in the previous slot, right? It will simply be a function of what was the last, maybe if it is more than certain time duration, it is simply a function of STSQ at t minus 1, right, for any t. And that is where it's saturated, it keeps dropping and saturates in some sense. And then we came up with this model where you can the same thing represented in a flow chart kind of, or a flow diagram kind of a setup, where you have the input available for your STSQs. We are predicting the STSQs, and then in case of rebuffering, we are depreciating it. If there are no rebuffering, we keep using the same model, and then we use this STSQ tilde for your TVSQ prediction, right? So we didn't change the TVSQ prediction model, we retained the same model, right, proposed earlier. And that is why we named it as eTVSQ or enhanced TVSQ, which is essentially a way of modeling or computing TVSQ while capturing rebuffering instances also. So that was our contribution in this particular work. And that was our first preliminary work, right? But then the challenge was, at that point of time, we were not able to find any database available which had really detailed rebuffering instances captured as part of the database itself. So we said, fine, why not, let's work in that direction. And I think again I should highlight here Dr. Ishwar and Dr. Sumona's contribution, because they're the ones championing the QoE and the video component of this work. So there was this effort performed at LFO VIA lab, which is essentially championed by Professor Sumona at IIT Hyderabad. It's a lab for video, and image analytics. And a database was created where the database consisted of 54 videos, which were full HD and ultra HD videos. There were time varying, and the time varying quality and rebuffering distortions were included, as part of the database. And a subjective evaluation was, conducted by introducing various QoE impairments in this database, in a continuous fashion, including rebuffering instances, right? So we had those 54 pristine videos, and then we added those subjective, changes, time varying changes, or rebuffering distortions into the videos itself, and created a bigger superset, and then used them for a subjective evaluation for quality of experience impairments. Different type of rates for use. For example, now these numbers may appear really small, so you can appreciate that how things change within a span of 5 years in or 3 to 5 years in video context. So at that point of time, 60 was we were looking at 60 as a good FPS. So 25, 24, 25, 30, 60 FPS. Now people are even talking about 120 and beyond. For the matter, for gaming applications, people are even looking at much higher FPS. And then we looked at different rates like 300 kbps, 600, all the way up to 9600 kbps, which essentially translates to UHD, right? So we had SD, HD, and FHD and UHD, different type of resolutions available, right? Most of the videos were short videos. So we looked at 2-minute length, because then getting these because we have to perform subjective evaluation, getting end users to participate in this study for really long videos is also tough. 2 minute videos, they may sit. We can request, it's academic environment, and we can request our students and colleagues to participate in this kind of a study pro bono. And for 2 minutes video, they may agree also for some, let's say 5 such 2 minute videos or 10 such 2 minute videos. Roughly 15 minutes, 30 minutes, we can convince and request and get certain number of participants. But for longer videos, really tough. So we focus on shorter video lengths, and we used FFmpeg as the encoding for these videos. And this whole database thing is available open source online, and also published in this work in IEEE Transactions on Circuits and Systems for Video Technology. And we also did a mix and match while introducing the rebuffering instances. We did a mix and match in terms of what kind of rebuffering durations to include. So we looked at 1, 2, 3, 5, 7, 9 seconds rebuffering durations, and how many such rebuffering instances to occur per minute. So for example, maybe 1 in every 2 minutes, that is 5.5 per minute, or 1 per minute, or 2 up till all the way 5 per minute, right? And they were randomly distributed. So we had a UHD, FHD, this kind of a grid we created, which is essentially a randomized grid, so that we have different types of videos, which we looked at here, different resolution of videos, and different duration and frequency of rebuffering instances spread across this whole buffet of videos available in this database. And then we tried to apply the following rate adaptation. So we looked at rebuffering duration, and based on that, we dropped the rate levels. Or if there is no rebuffering happening, we kept on increasing the rate levels in this fashion. This is one example set. You can look at various other ways for these kind of rate levels or rate adaptations also. Now, please note, so again, I'm projecting image here instead of video in interest of time, because for if I start playing all those contents, it significantly increases the duration of the presentation. So here, for example, with pre-buffering, we have some sort of a PSNR measurement, because we're looking at the image in some sense, right? And then the frame during rebuffering, and then post rebuffering, you can again compute the PSNR. And there is a drop, right? There's at least a 10 dB drop, for example, in this case. And now, please note, we were able to capture this because we conducted our own continuous time QoE collection in this database. We are able to measure this continuous time QoE, and that is a really important part of the study conducted by Dr. Ishwara, where essentially we had 21 subjects using Slider app. So he designed the whole app himself, and we helped him through the overall process. But really good effort at his end, and it involved essentially using this slider kind of approach to rate the continuous QoE, right? And he followed this ITU 17 recommendations, and the rating was translated into a number from 0 to 100, where 0 is worst and 100 is the best video quality. And as you see here, so this is from the actual database study itself that we conducted. You have a playback state where, as time elapses, the with playback, the QoE improves and then saturates at a certain point, and then it fluctuates based on various time varying components, except at rebuffering. At rebuffering, it drops, and as you see here, it does drop exponentially. So the previous assumption that we had that of an exponential drop was a very valid assumption, right? And now when we look at it at hindsight, that we were able to capture this effect even before creating the database to a certain extent, based on intuition and based on the past experience we had with network phenomena. And then again, when playback restarts, it starts rising, and there is again a slight exponential kind of trend in the increase in playback, and then it saturates again around a certain level. Now, this is where the machine learning part comes into picture. So we used various machine learning models. For example, in the first one, we started with SVR, support vector regression in playback state with Gaussian kernel. And then we used an exponential QoE depreciation in rebuffering state. We were already having this motivation, but now with this data available, we were able to see that indeed the exponential model really captures the depreciation well. So we used an exponential QoE depreciation in rebuffering state. And then we can have these toggling between these two states. We can have playback or rebuffering, and then based on that, we can decide which model to use, right, to capture. So I'll not go too much into the details in interest of time, but if any one of you is interested, I'll be happy to discuss maybe offline or maybe towards the later part of the presentation. So this is just one of the ways to capture the QoE for this particular model, where the two key features we use for training the model is STSQ and the first order QoE feedback, right? And in rebuffering state, we had an exponential depreciation similar to ETVSQ that we have done earlier, where QoE at time t e to the power minus, some parameter you can say here, which parameter obviously we computed this using a linear relationship between QPRB, and we also computed these linear coefficients P0 and P1 based on the database. We tried to compute this, and we even checked this. It's not that we only did this study for our own database. I'll have more results going forward where we show the performance of this on existing other databases without rebuffering. And by the time we conducted and completed this study, others also, that's the important and the fun part of the research. You're never alone in these interesting things. There is always another group who is also trying this at the same time. So there was another group trying at the same time, and there are several other databases now available in the literature which capture rebuffering. So going forward, I will present other works that we did with Dr. Ishwara and others as part of this collaboration, where we not only tested this for our own database, we also test different ML models we propose for all the other databases which came up by that time, which also contain rebuffering instances. So this was the preliminary results we had for SVR, QoE, right? And because at that point of time, there was no other model available, we compared with ETVSQ, which was our own model, and we were able to show it performs with various VQA metrics. It performs, reasonably well, right? For the matter, for example, RMSE, you look at, maybe I'll pick RMSE here. RMSE is really much smaller than the ETVSQ. Right? And one of the reasons is because ETVSQ was just based on intuition. At that point of time, we are just using the intuition that an exponential depreciation should probably happen in quality of experience. Whereas when we proposed a SVR-QoE model, we knew based on the database what kind of exponential decay we should be using for rebuffering instances. And that is why this enhancement in performance, right? And then you can also do this with the, with the actual ground truth, because we have that available as part of the database, the blue line, and then the predicted one is the red line through this SVR QoE. Within the 95% confidence interval, we are plotting the 95% confidence interval also. And then as you see here, ETVSQ is also there. It is not capturing it well, but in terms of trends, the interesting part is, although it's just a model based on intuition, pure intuition, it still works reasonably well. The ups and downs are captured reasonably well, but the rate at which the SVR QoE was able to catch up to actual ground truth is much better. As you see, the red and the blue lines are much better correlated, for example, than ETVSQ, right? Whereas this is true for rebuffering instances, because this is kind of like a rebuffering instance. But for non-rebuffering instances, for example, in the second figure on the right side, you see, they're more or less similar. There's not significant difference. You can have multiple rebuffering instances, and with multiple rebuffering instances, or when you increase the frequency of rebuffering, ETVSQ simply dies out. Earlier, we had only one or two. But now as you increase the rebuffering instances, again, the proposed model was performing reasonably well, but much better as compared to ETVSQ, as you see here. And the same can be observed. You can also compare existing other models. For example, there was an HW model already available. You can compare the performance, and for all the performance metrics at that point of time, the proposed SVR-QoE turned out to be a much better model, especially with STRED as the VQA metric. So we also evaluated across multiple VQA metrics like MSS, SIM, or NIQE, right? And so this is just a comparison with the state of the art, but of course, it's a reasonable comparison, because HW doesn't capture rebuffering, right? So it's not able to capture very well the ups and downs or the valleys, coming because of the rebuffering. Now, as I mentioned, there were several new databases for QoE, and a lot of them parallelly came up with their own subjective video quality assessment. They have their own models, and they have their own types of videos available in the dataset, types of rebuffering instances also in one or two of them. So then just a summary. Again, this is a slightly older summary. Things have evolved since then, but if you look at it, the live QoE or the TVSQ data set, which was already there, it captured time varying quality, did not capture rebuffering. The videos are openly available, but the metadata was partially available. The live Netflix database captured rebuffering, the time varying quality also, but the video availability was only partial. Only a part of it was available at that point of time, and the metadata was available. Now the proposed model by Professor Sumona's lab whereas I was also collaborating in this work to a certain extent. The TVQ, the rebuffering, video quality, as well as metadata, all four are present. And similarly, there was a mobile stall2, live mobile stall2 database which had rebuffering, and videos were available, metadata was available, but the time varying quality was not available, right? So just to position the work that in this case all four things were available. Then as another model was proposed by our group, which was on based on long short-term memory, or popularly known as LSTM models, right? So this was, and the motivation for this work was that when we are trying to look at the video quality, there is a long-term memory or hysteresis effect happening, because we are consuming a certain type of content, it is at a certain rate, and if everything is going well, there is no rebuffering happening, there is a long-term memory in the system. But at the same time, the time varying quality in the short term also affects the quality of experience. So if we can capture both somehow, the long and the short term memory effect of quality of experience, that could probably lead into better measurement, or better capturing the quality of experience. So motivated by that, this kind of LSTM based approach was used, multi-layered, 2 layers in this case was used, with different, I think 22 units. There was an optimization done over the number of layers and over units also, but I will not go into that much level of detail here in interest of time. And here again, with rebuffering, we are trying to capture what happens to, for example, the STSQ, the short-term subjective quality, right? And then there is a playback indicator, which essentially is staying in rebuffering case, it goes to 0. There is no playback happening. If playback is happening, indicator is 1, right? And then we can also have something called the time elapsed since last rebuffering. So this was another thing we thought, we figure out affects our quality of experience. If it has been a while since there is no rebuffering happening, it affects as an input, what is our current quality of experience. And this was motivated by, for example, this result, where we were able to show that frequent rebuffering instances also significantly affect the quality of experience, right? So motivated by that, we came up with this LSTM based model, and we were able to show that. So we compare it with now some more state of the art works available. For example, NLSS QoE was again another work proposed by us, and then NARCS QoE was available. And if you look at the performance metrics in terms of OR, obviously the NARCS QoE model is the best. It has the least OR over across all VQA metrics. But in terms of the LCC, SROCC, or RMSC, for example, the root mean square error here is the least, 7.78% for LSTM QoE with STRRED as the VQA metric. So we are able to show that at least for majority of the performance metrics, our model is better, and it is in some sense a competitive model, at least, right, compared to the state of the art at that point of time. And we compare again, with the different type of. Just a second. So maybe these are again the results coming from the same work. In interest of time, I think I'll move on, and just to highlight, how it captures. So if you look at the ground truth and the predicted, QoE, because we have different databases, right? So these are essentially the 3 tables I have, or 4 tables I have, is based on different databases available, because I have these 4 databases available, for example. So we compared over all 4, and across all 4, the LSTM QoE turned out to be competitive. And at least for some of them, for example, for this one, it was the state-of-the-art model for this database, at least, because with different databases, the performance can vary. So we performed comparison across all of them, and we were able to show that either it is state-of-the-art model for a database, or at least it is competitive enough to be state-of-the-art for certain VQA metrics, right, across different type of databases. Same thing is highlighted here in terms of the predictions compared to the ground truths, and just to highlight how it very accurately captures the QoE during rebuffering instances also, right? And again, this is for various databases. We're able to show how the performance of the proposed LSTM model was really good. So so we were able to show it is indeed so here we are just comparing with whatever is the best available. Either LSTM QoE was the best for that particular database, or it was the second best, typically. It's only a metric, for example, for live mobile stall2 database, the NLSS QoE, the standard deviation of OR was lower than ours. But by and large, it was really competitive at that point of time, the proposed LSTM QoE. So then we said, fine, now we have a really state-of-the-art model to capture QoE, which captures both long and short-term effects. Can we now use it to perform resource allocation? Because that is the original problem we started with, right? For that matter, that was the reason why Professor Sumona and Dr. Ishwara and others, they approached me, because I work predominantly in this domain of resource allocation for wireless networks. So this is the original problem which we started it in 2014 kind of a time frame, right, where we wanted to optimize resource allocation for video users over a cellular network. So we revisited the same problem, and this time we said, fine, the earlier assumption of having a proxy server and all is not very practical. Typically, if you're using a QoE model, we can only do these kind of adaptations at the client level, because when we are playing, for example, a dash based architecture, or for example, we are using YouTube, the dash client is sitting in our device. So the device should be the one requesting content, and then adaptation should be happening at a dash server. And then eNode B can only know what kind of content we are getting. We can send some minor feedback to the eNode B, but at the end of the day, the resource allocation is happening at the eNode B, for example, for downlink. So then based on this, we tried to come up with this kind of a QoE based resource allocation, where for a eNode B, it is performing QoE based array. It requires some QoE information, but please note this QoE information is not very large in terms of amount of data. It's really small. For example, if you're looking at those numbers 0 to 100 on a scale of every 1 second, it's a reasonably small. It's a few bits per second, right, of data coming from each dash client. Now each dash client is going to send some QoE features to this continuous QoE prediction model. It's going to come back with some QoE number which the dash client can feed to the eNode B, and based on this, the eNode B can decide what kind of resources to allocate to this dash client, right? And we came up with a alpha fair kind of a utility model, where this alpha fairness is important, because we don't want that only the best QoE users hog up the network. So if we start using at some rate or some QoE kind of a setup, typically there is this fairness issue which comes into picture, that good users keep getting better and poor users start becoming poorer. So we don't want that in the setup, right? We want to have some notion of fairness. So we used an existing alpha fairness kind of an approach, and with varying alpha, you can actually achieve varying or degree of fairness. For example, for alpha equal to 0, this boils down to some utility or some rate. So we looked at multiple factors. We looked at the cumulative average QoE for the user. We looked at the average throughput. What is the average throughput in terms of data rate? What is the per sub channel throughput for each user? And based on this, now we try to, let's say, maximize alpha fair objective function, where we are trying to capture through U alpha RTH each ith user's utility from that particular rate, right? And then this is subject to certain constraints. For example, here for simplicity, we are doing sub-channel allocations, but you can also translate this to OFDMA-based allocations. So we have maximum number of capital S sub-channels, and each user I is allocated SIT sub-channels in the time instance T, and the summation of all this allocation should be less than the available number of sub-channels. The allocated sub-channels to a user cannot be negative, so they have to be greater than or equal to 0, and it belongs to a set of, in some sense, positive or non-negative integers, right? And then there is a relationship between the utility and the data rate. For example, we can have RITH as the rate and SIT as some subjective video quality input we are feeding back. So we want to capture both, in this model. And so this was a simple rate-based allocation, where we have rates, and some sub-channel allocations, right? And then instead of this, we can use a QoE-based approach, which we have discussed so far in today's discussion, where we can, instead of feeding in the rate, we can feed in the QoE, QIT, and then try to perform the same optimization, right? And so these are just standard compliant, obviously slightly older version of LTE. And now if you look at it, it is release 9. We are now talking in 5 years, release 17 and all. But at that point of time, this was a more state-of-the-art release available. And we use this to perform resource allocation. So 180 kilohertz sub channel, and typical LTE parameters. I'll not go into too much detail of this. This is more from wireless communication background, but I'll be happy to answer if there are any queries in this direction. And we performed resource allocation. We computed various network level QoE with varying level of delays, for example. And the throughput array typically performs inferior to QoE based array. So we were able to show that a throughput based approach for resource allocation has significantly lower quality of experience as we vary alpha, which is the fairness parameter. For alpha equal to 1, typically the two merge. which was a very interesting observation. So for proportional fairness, essentially alpha equal to 1 translates to proportional fairness. For proportional fairness kind of a scheduling approach, or equal resource allocation kind of a scheduling approach, the throughput based RA and the QoE RA, they were overlapping in performance in terms of quality of experience across the network, right? On the other hand, for less or more alpha, typically you will see that the QoE based resource allocation dominated in terms of performance, right? Especially with increasing delay, the gap widens. We can also, for certain values of alpha, we are projecting here with different number of sub-channels available per user. We try to increase the resource available in the system. And here the interesting thing is, on the left hand side, there is a gap in performance, right? For lower alpha, for example. But as we keep increasing alpha, with increasing number of available sub-channels or with increasing number of resources, the two starts to converge. Now, you can also view this result in the perspective of, if there are sufficient resources available in a setup, if there are sufficient resources available in our network, then there is not much difference in throughput optimization or QoE optimization. However, when the resources are constrained, when the number of resources available per user are less, then the quality of experience when obtained from a QoE optimization perspective, or a resource allocation done with QoE as the objective, right, performs much better than the throughput based allocation, right? So there is a gap in performance between the two, especially for lower resource availability regime. With reasonably large number of resources available, they start to appear similar, right? Same thing for other values of alpha, just to highlight that it's not restricted to what value of alpha we choose. For any value of alpha less than 1 or greater than 1, there is a gap when the resources are constrained. But as we keep improving the available resources, then the two coincide. Another way to look at it is, if we have a resource constraint regime, maybe we should be using a QA based optimization. But if we have sufficient resources and there are low number of users, for example, with good number of resources available, maybe in that kind of a regime, a throughput based optimization suffices, right? So even so we just compare here the performance using the proposed method. We call it Vicara, based on video streaming adaptation based on subjective quality. So here with SVR QoE, we are showing the results. We can also generate the results with different other models that we have for different values of alpha. And I'm just skimming through this part, because essentially we're changing the model, because we initially started with the SVR QoE and then we went on to LSTM, and even for LSTM based approach, we were able to show that the proposed QoE based architecture for resource allocation turns out to be much better, right? So in interest of time, I think let me not exceed the 1 hour allocated to me, or 1.5 hours allocated to me. Maybe I'll take I'll stop here the presentation. I'll be happy to take any comments or discuss things in detail. Yes.
If any doubt or query, please ask. Any question from the side of participants?
So I'm also sharing my email ID. I'm projecting it on the slide. I'll also type it in the chat window in case if later you have something, if you want to collaborate something in this direction or something similar, please feel free to reach out to me. We are always looking for collaboration. Another motivation for us to participate in these kind of talks is to maybe request prospective students. So if you know somebody who wants to pursue graduate studies, who is looking for a master's program or a PhD program, we have a very active master's and PhD program at IIT Hyderabad in general, and in our department in particular. For the matter, we have more graduate students than undergraduate students at IIT Hyderabad. I think close to 55% are graduate students. Amongst them, I think more than 25% are PhD students. And within EE department, I think we have around 200 plus PhD students. So we are actively looking. There is really good amount of funding available. We do have good competitive scholarship also available for students. So if you know someone who wants to pursue graduate studies in communication, signal processing, or anything related, please feel free to reach out to me. and I'll be happy to help, or I'll be happy to redirect you to other faculty members who might be working in your domain. And this is also a request for all the faculty members who are participating in this particular program. If you know some good students and you can recommend some to us, please do. We are always open to you know any sort of collaboration through research and otherwise. Yes.
So I think no question from the side of participants. Thank you, sir. Thank you sharing your wide experience with all of us. And I'm sure this experience will guide us, all of us, to find new areas or explore the new areas in the field of adaptive video streaming. Thank you, sir. Thank you.
Sure. Thank you. Thank you again for inviting me. It's always a pleasure. Thank you. Thanks a lot.
So, dear all, this is the second session, and this is the end of this session, and we will resume tomorrow around 10:55. Thank you, all of you. Please submit the feedback form also. Okay, we are sharing the feedback link. Thank you, all of you. I shared the Google form for feedback. All of you are requested to please fill this form.
Sir, we have not received the feedback link for the first half, I guess.
Okay, we will also share that.
All right, sir. Thank you.
Okay. Thank you for reminding us.
Hello, Sachin sir.
Yes, sir. Yes, sir. We have shared the feedback form with all the
Uh-huh.
participants. So they are
Mm-hmm.
filling second session. Sir,
Yes, sir.
can we share the feedback form for session one also?
Yes, yes. Yes, we should share it.
Okay, okay, okay.
Yeah.
I'm
So just we can give them the link. They will fill it, right?
okay, sir. Okay, sir.
Yeah, sure, sure. So anyway, they can fill it later on and submit, right? That's just a Google form.
Right now they are submitting for session two. So
Okay.
we will share on the WhatsApp group. So they will.
Yeah, just on the WhatsApp group you can share, and then they will submit it, right?
Yes, sir. Yes, sir.
Yes, yes, right.
We will share the feedback link of previous session on the WhatsApp group. Okay. So right now you fill this session feedback form, or you can fill later on. We will also share the session 2 feedback form also on the WhatsApp group. So if anyone is remaining, so you can fill on that link. Okay. And today's sessions are over. And if you have any doubt or any query regarding anything, so you can mail to us, and we will resume on tomorrow at 10:55. Thank you all of you. You can leave now. Thank you all of you.